morning, students. In today's class we shall study how to find out the derivatives of inverse trigo functions. So derivative of inverse trigo functions. So let us start with the sine inverse function. Say y is equal to sine inverse x. Now when we write down the equation this way, we know that x belongs to the closed interval minus 1 to 1 and y belongs to the principal branch of the sine inverse function, which is the closed interval minus pi by 2 to plus pi by 2. Now to find out the derivative, let's write down the equation like this. Sine y is equal to x and differentiate both sides with respect to x. So we know this is a composite function, hence its derivative would be cos y dy by dx is equal to 1, or we can write down dy by dx is equal to 1 upon cos y. Now here cos y can be written as under root of 1 minus sine square y. Now see, when we write down cos y here, look at these angles minus pi by 2 and plus pi by 2. So when we are writing like this automatically means that y cannot be equal to plus minus pi by 2, because if y is plus minus pi by 2, then the derivative is basically not defined. So we are eliminating these two angles. The moment we eliminate these two angles, automatically x will also not be equal to plus minus 1. This will be clear from the next step also. 1 upon under root 1 minus sine y is x, so we can write down x square. So if x is plus minus 1, again this expression will be not defined. So hence we know if y is sine inverse x, the derivative is 1 upon under root 1 minus x square. So the result is what I am going to write down here. The first result, y is sine inverse x, so this implies derivative of sine inverse x function will be 1 upon under root 1 minus x square, where x belongs to open interval minus 1 to plus 1, cannot be minus 1 or plus 1. Okay, so this way from this equation we have found out the derivative. Restricted values of x and y, we are able to find out the derivative. Now in a similar manner, let us find out here derivative of y is equal to cos inverse x. Here again x belongs to this closed interval and y belongs to the principal branch of the cos inverse function, which is the closed interval 0 to pi. So the equation can be written as cos y is equal to x, differentiating both sides with respect to x. This is what we get, hence dy by dx is minus 1 upon sine y. Now here you know y cannot be 0, because in that case derivative is not defined. Likewise y cannot be pi also. So here we know the restriction is y cannot be equal to 0 or pi. Then moving to the next step, sine y can be written as under root of 1 minus cos square y, and we know cos y is x, so we are getting the result minus 1 upon under root 1 minus x square. Here we know x cannot be equal to plus minus 1. So that means if y is equal to cos inverse x, then the derivative of cos inverse function would be minus 1 upon under root 1 minus x square, where x belongs to open interval minus 1 to plus 1. So you have to just take care that for the inverse trigo functions, what are the possible values of x in which the derivative is possible. This is what is to be remembered. So next, let's find out derivative of y is equal to tan inverse x. Here we know x belongs to real numbers and y is the principal branch of the tan inverse function, which is the open interval minus pi by 2 to plus pi by 2. So the equation can be written as tan y is equal to x, differentiating sec square y dy by dx is 1, which means dy by dx is 1 upon sec square y. Now here both these angles are not included, so there is no problem to the sec function here in this branch, and sec square y can be written as 1 plus tan square y, and we know tan y is x, hence the derivative of tan inverse function is 1 plus x square. This term will always remain positive, so that means x can be any real number like it was here. So the third result that we have got is, if y is tan inverse x, then the derivative of the tan inverse function is 1 upon 1 plus x square, where x belongs to the set of real numbers. Let y be equal to cot inverse x. So we shall have here cot y is equal to x. Here we know x will again be a real number and y will be the principal branch of the cot inverse function, which is the open interval 0 to pi. So differentiating, derivative of cot function is minus cosec square y dy by dx. Right side derivative is 1. So we get here dy by dx is minus 1 upon cosec square y. Cosec square y is well defined for this range of angles, and cosec square y can be written as 1 plus cot square y, where we know cot y is x. So this result is minus 1 upon 1 plus x square, where x is again any real number. So the fourth result that we have got is, if y is cot inverse x, then the derivative of the cot inverse function is minus 1 upon 1 plus x square, where x belongs to R. Then y is equal to sec inverse x. Now here x is set of all real numbers except minus 1 to plus 1, and y is the principal branch of the sec inverse function, which is the closed interval 0 to pi except the angle pi by 2. So equation is sec y is equal to x, differentiating. So derivative of sec y is sec y tan y dy by dx is 1, which means that dy by dx is 1 upon sec y tan y, and here this tan y we can write down as square root of sec square y minus 1. So here it is, if we replace sec y by x, so it is 1 upon x under root x square minus 1. So here you know x again cannot be minus 1 or plus 1, which is this. Alright, that we have already mentioned. So the derivative of the sec inverse x function is this. So if y is sec inverse x, then derivative of the sec inverse x function is 1 upon x under root x square minus 1, where we have mentioned x is all real numbers except the closed interval, because it cannot be plus 1 minus 1. That's what we have included. All these numbers deleted from here would be possible values of x. Then likewise we move on to y is equal to cosec inverse x. For this also we know x will be the set of all real numbers except this, and the principal branch of the cosec inverse function is the closed interval minus pi by 2 to plus pi by 2 except the angle 0. So the equation can be written as cosec y is equal to x. Differentiating both sides with respect to x, we get minus cosec y cot y dy by dx is equal to 1, which means dy by dx is minus 1 upon cosec y cot y. And here cot y we are writing as under root of cosec square y minus 1. Since cosec y is x, the expression can be written as x under root, in the denominator it can be written like this, where we again know x is not equal to minus 1 plus 1, so that this expression remains a well-defined expression. Moreover, there are more conditions on x that we'll write down here. If y is equal to cosec inverse x, then the derivative of cosec inverse would be minus 1 upon x under root x square minus 1, where x belongs to all real numbers except this open interval. So for the last two results now, you will see that here in the result I've only mentioned that x is not minus 1 and plus 1, because then this radical sign will make the derivative not defined. Whereas if you see here, all real numbers in this category are also not possible. So what is possible here for the derivative of sec inverse or cosec inverse function? All real numbers except this. You can compare what is the value of x here for the sec inverse function, values of x for the cosec inverse function. Here plus 1 minus 1 are included here and here, but when you are finding out the derivative, we have excluded plus minus 1. That's what we have to take care of. So these are basically 6 standard results here. You must have noted that these are all standard inverse trigonometric functions. So the results are written only for standard inverse trigonometric functions, but in case we have composite inverse trigo functions, then the process can be slightly different. We can solve the questions in two ways. Either use these results to find out derivative of composite inverse trigo functions, or second method where we simplify the composite functions first and then find out the derivatives. So it is a second method which is an easier method, and that's what we are going to follow up and use this method to solve questions from exercise 5.3. So we are solving questions from exercise 5.3, and the first question that we are taking up is y is equal to sine inverse 2x upon 1 plus x square. Now you can see here the standard inverse trigo function is sine inverse x. This is not sine inverse x, so we can easily make out this is a composite function. Hence the second method says that we need to simplify the function x, and simplification is possible if we use some substitution. And to use these substitutions, we have to be very alert on the trigonometric identities that we have learned over the years. So if we substitute x is equal to tan theta here, then this equation can be written as y is equal to sine inverse 2 tan theta upon 1 plus tan square theta. So if you remember the identity, then you will remember that 2 tan theta upon 1 plus tan square theta is actually sine 2 theta. If you remember, you can directly substitute it here. In case you don't remember, then convert tan function into sine and cos. So the function can be written somewhat like this. Cos square theta plus sine square theta into cos theta, like this. So when you have converted tan into sine upon cos, you get this, where the denominator you can see is 1 and the numerator 2 sine theta cos theta will give you sine 2 theta. Since we are working in the principal branch here, there is no restriction on x given here, so we know in the principal branch this value has to be 2 theta. So the equation which was this now reduces to y is equal to 2 theta, and from here we can find out what exactly is theta. Theta is tan inverse x. So when we differentiate y, that means we are differentiating the tan inverse function, which is the standard function, and from here we get to know the result is 1 upon 1 plus x square. So this is the derivative that we have obtained. If we do not do this kind of a simplification, the function will not reduce to this form and the derivative will be very difficult to be found. So if we are not using substitution, the process will become more cumbersome. It's not that it cannot be found. It will be a very long time consuming method. So the best method would be, the moment you see that it is a composite function, use a suitable substitution and then simplify the function and hence differentiate it. Now when you're using a suitable substitution, all the trigonometric identities should be there in your mind. You look at a function and you should be able to identify whether the substitution is sine theta or cos theta or something else. The next question from this exercise is y is equal to tan inverse 3x minus x cube upon 1 minus 3x square. Here we are given that x is greater than minus 1 by root 3 and less than 1 upon root 3. So here again this is a composite function, so some substitution has to be used. Let us use x is equal to tan theta. So y is equal to tan inverse 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta. So once again, the substitution will come into your mind only if you remember what is this formula here. So this formula is basically tan 3 theta, and the result will be equal to 3 theta if this angle belongs to the principal branch. Here is a restriction on x. So let us check, is this possible or not? X is tan theta, so replace x by tan theta. Tan theta is greater than minus 1 by root 3, less than 1 by root 3, because tan theta is an increasing function. So we can write it down as tan inverse minus 1 by root 3. Here is tan inverse 1 by root 3. So since we know how to find our principal branches, this value is minus pi by 6. Here it is plus pi by 6. So we have got an angle theta. What we want is 3 theta. So multiply by 3 and we get here, multiplying by 3 we get minus pi by 2. Here we get pi by 2. So we know this angle belongs to the principal branch of the tan inverse function. Hence this result can be written as 3 theta, or from here theta is tan inverse x. So now you can see this complicated function where we had a composite inverse trigo function, with this substitution converts to a standard trigo function where differentiation is easily possible. 3 times derivative of tan inverse x, the result is there. So we know it is 3 upon 1 plus x square. Next question from the exercise is y is equal to cos inverse 1 minus x square upon 1 plus x square, where it is given x is greater than 0, less than 1. So again a composite function, simplification required. Let x be equal to tan theta. So y is equal to cos inverse 1 minus tan square theta upon 1 plus tan square theta. Again, you have to remember the identity, and this identity is basically cos 2 theta. So the result will be equal to 2 theta if this angle belongs to the principal branch. Let us check. X is tan theta. So tan theta greater than 0, less than 1. Because tan theta is an increasing function, so theta can be written as tan inverse 0, and it is less than tan inverse 1. So theta is greater than 0, less than pi by 4. Our angle is 2 theta, so multiplying by 2 we get this. So we observe that the angle, it belongs to a subset of the principal branch of the cos inverse function. Alright, subset. Hence this can also be written as 2 theta, or y is equal to 2 times tan inverse x. So with this substitution, once again, a composite inverse trigo function can be written as a standard trigo function, inverse trigo function, and hence the derivative is 2 upon 1 plus x square. So in all these questions, it is important to use some substitution here. Identities have to be remembered. Next, we have to always cross-check that the angle belongs to the principal branch or a subset of it, and hence using standard results, the derivative can be easily found. So next is y is cos inverse 2x upon 1 plus x square, where x is greater than minus 1, less than 1. So once again, composite inverse trigo function. Let us substitute x as tan theta. So y is cos inverse 2 tan theta upon 1 plus tan square theta. The identity here is for sin 2 theta. So you know this result cannot be 2 theta because we need cos inverse cos of some angle. Alright, so that means the sine term has to be converted to cos. So we can write it down as cos pi by 2 minus 2 theta. Now this result will be equal to pi by 2 minus 2 theta if this angle belongs to the principal branch. So let's check. Here x is tan theta. Tan theta greater than minus 1, less than 1. So I'll write down here theta directly, greater than minus pi by 4, less than pi by 4. We want minus 2, so we are multiplying by minus 2. So these signs will change. Greater than will become less than, this will become greater than. Multiplying by minus 2, we get pi by 2. Here again we are multiplying by minus 2, so it becomes this. I'm just going to add pi by 2 here. So pi by 2 minus 2 theta, adding pi by 2, this becomes pi. Here adding pi by 2, it becomes 0. So as is a norm, we usually write down the greater than values on the left side. So the angle is greater than 0 and is less than pi. So you can see here that this angle belongs to the principal branch of the cos inverse function. Hence y can be written as pi by 2 minus 2 theta, which means it can be written as pi by 2 minus 2. Theta is tan inverse x. Alright, and hence when you differentiate, derivative of constant is 0. Here minus 2 into derivative of this, which is 1 upon 1 plus x square. So next question is y is equal to sine inverse 2x under root 1 minus x square, where x is greater than minus 1 by root 2, less than 1 by root 2. So here again, composite inverse trigo function, so some substitution has to be used. So if we use here x is equal to sine theta, then the function is 2 sine theta under root 1 minus sine square theta, and we know this is under root 1 minus sine square theta will become cos theta. Again using the standard result, this is sine 2 theta, and now this angle will be equal to 2 theta if this angle belongs to principal branch. So substituting x, which is sine theta greater than minus 1 by root 2 less than 1 by root 2, because sine is an increasing function, so it can be written as theta greater than sine inverse minus 1 by root 2 less than sine inverse 1 by root 2. And the principal branches, according to principal branches, this angle is minus pi by 4, this is pi by 4. Our angle is 2 theta, so multiplying by 2 we get the angle greater than minus pi by 2 less than pi by 2. So this angle belongs to the principal branch, or this is a subset of the principal branch of the sine inverse function. Hence y is 2 theta, and this can be written as theta from here is sine inverse x. So the derivative would be dy by dx. Derivative of sine inverse function is 1 upon under root 1 minus x square. So this is the derivative obtained. Now while solving this question, I think an idea must have come into your mind that instead of substituting x as sine theta, we can also use here x as cos theta. So let's just try. If we substitute x as cos theta, then y is equal to sine inverse 2 cos theta under root 1 minus cos square theta, which is 2 cos theta sine theta. Using standard results, this is sine 2 theta, and hence y should be equal to 2 theta once again if this angle belongs to the principal branch. Let's check the principal branch. This is the information given. So replacing x, what is x here now? Cos theta. So cos theta is greater than minus 1 by root 2 less than 1 by root 2. Because cos is a decreasing function, so these signs will change. Okay, I've changed the signs. Cos inverse minus 1 by root 2. This will be cos inverse 1 by root 2. So theta is less than. Now since we know how to find out the principal values of cos inverse minus 1 by 2, I'll write it down directly. It is pi minus pi by 4, which is 3 pi by 4, and here it is pi by 4. Okay, and our angle is 2 theta, so 2 theta multiplying by 2, it is 3 pi by 2, and here it is pi by 2. Just changing the order here, so 2 theta greater than pi by 2 and less than 3 pi by 2. So from here you directly understand that this angle does not belong to the principal branch of sine inverse function. If you can directly look into that, fine, or else in the coordinate system, see, angle is greater than pi by 2, that means the angle is in the second quadrant. Less than 3 pi by 2, that means third quadrant. So this angle belongs to the second or the third quadrant, which is not, these are not the quadrants belonging to the sine inverse function. Hence this angle 2 theta, the angle 2 theta does not belong to principal branch of sine inverse, hence y is not equal to 2 theta. So what it basically means is x equal to cos theta cannot be used. Alright, so although when you look at an expression of this kind, you simplify, you will get sine 2 theta. Things seem to be simple, but if you check out this way, you get to know that the angle does not belong to the principal branch of sine inverse function. Hence, any substitution is not possible. It has to be a validated, justified substitution. The last question that we take from this exercise is y is sec inverse 1 upon 2x square minus 1, where x is greater than 0 and less than 1 by root 2. Composite inverse trigo function. So let x be equal to cos theta. You know there's a formula for 2 cos square theta minus 1. That's why we have chosen this substitution. So y is equal to sec inverse 1 upon 2 cos square theta minus 1, and 2 cos square theta minus 1 can be written as cos 2 theta, which is sec 2 theta, and then y will be equal to 2 theta if this angle belongs to principal branch of sec inverse function. Let's check that. So substitute x is cos theta. Now we know cos is a decreasing function, so theta, these signs will change, less than, greater than, alright. So cos inverse 0, cos inverse 1 by root 2, so theta is less than cos inverse 0 at pi by 2, and cos inverse this at pi by 4. Our angle is 2 theta, so multiplying by 2, this is pi, and this is pi by 2, and writing it down in the right order, 2 theta greater than pi by 2 less than pi. So that means greater than pi by 2, second quadrant, less than pi, second quadrant. And that second quadrant we know is the principal belongs to the principal branch of sec inverse function. Hence y is 2 theta, which is theta is cos inverse x. That means the derivative is minus 2 upon under root 1 minus x square. So this is how the derivatives of inverse trigo functions have been obtained. You just have to remember one simple concept here. The moment you come across a composite inverse trigo function, think of substitution and simplifying the function before you differentiate it.